All right, so again, a lot of vocab in this chapter. The concepts are not difficult, but if you don't familiarize yourself with the terms, it's going to get super confusing because we're going to learn about a lot of different types of segments and then theorems based on those segments. So a lot of new words, a lot of vocab, okay? Not a lot of hard arithmetic. The first two that we're going to talk about in 5.1 and again in 5.2 are perpendicular and angle bisectors. So hopefully things we've heard of before, but now we're going to learn about them, what happens when you get into a triangle. Mm-hmm. So the word equidistant, okay, if you break it up into its parts, equa and distant, means that it would be equal distance from an object. So when a point's the same distance from two or more points or objects, the point is said to be equidistant from the object. There's the pen right there. You can use back. Some of you guys need to work on your spelling skills. Equidistant. Okay, it's a good thing I don't. Okay, second term is perpendicular bisector. So again, if you break that apart, hopefully you know what that means. The perpendicular part means right angle. Bisector means cuts it into two congruent parts. So a perpendicular bisector is a segment, ray, line, or plane that's perpendicular to a segment at its midpoint. So in this drawing, you can either say segment CP or ray CP or line CP, any of those, segment, line, ray, is the perpendicular bisector. Of segment AB. Can you bisect a line? Yes. Would a line end? No. How would you find the middle? You can't. So can you bisect a line? No. Can you bisect a ray?
Yes.
Does a ray end? No, it doesn't end, right? It goes on in one direction, but you can't find the middle of a ray. So the only thing that can be bisected is a segment, okay? So on this, we can't say the reverse. I can't say AB is the perpendicular bisector of line CP. One, it's not marked as congruent parts. Two, that doesn't end. So you can't find the middle of it. Okay, perpendicular bisector theorem says in a plane, if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of that segment. So from any point on the perpendicular bisector to the endpoints of the segment that is being bisected would be congruent. So from that diagram again, which one is the perpendicular bisector? CP. And which one is being bisected? AB. Good, right? So the perpendicular bisector is CP. The one that's actually being bisected is AB. So this theorem tells me any point along CP, which is my perpendicular bisector, would be equidistant from the endpoints of the perpendicular of the segment that's being bisected, which would be AB. From that information, you could say that AC is congruent to CB. P is also congruent or equidistant from AB, but that's already marked, right? But if I put another point, let's say I labeled a point down here and I put point M, M would also be equidistant from A to B. So AM would also be equal to MB. So from any point along the perpendicular bisector, it would be equidistant to the endpoints. So from that point to the endpoint would equal that point to the other endpoint. Okay, converse of the perpendicular bisector. What happens when you do a converse to an if-then statement? Do you remember? What's the converse? I hope somebody remembers it because it's on your midterm, right? What happens when you do the converse? Switch the order, right? So if it was if then, the converse switches what's after the if with what's after the then. So we switch the order here. So the last one said if it lies on the perpendicular bisector, then it's equidistant. This time we're saying if a point is equidistant from the endpoints of the segment, then it lies on the perpendicular bisector. So we switch the if and the then. So in the diagram that's there, we know D is equidistant from A and B. So my then here would be, so because D is equidistant from A and B, and we know that because AD is marked as congruent to DB, then D lies on the perpendicular bisector.
Wait, is that A plus B?
A and B.
Wait, what is that between B and C?
That's an and symbol.
Oh, okay.
So because D is equidistant from A and B, D, so we don't need the then. I'll put D lies on the perpendicular, the upside down T there is perpendicular bisector of AB. So this is the converse. The initial one said if it lies on the perpendicular bisector, then it's equidistant. This one says if it's equidistant, then it lies on the perpendicular bisector. So you flipped the if and the then. So you might be asked to justify your steps, not necessarily in a 2-column proof, but give the reason for your answer. The initial one is the perpendicular bisector, and this one is the converse of the perpendicular bisector. Okay, a locus. So a locus is a set of points that satisfies a given condition. Another just vocabulary term here that you're going to see in the definitions. So the perpendicular bisector of a segment can be defined as the locus of points in a plane that are equidistant from the endpoints of the segment. All this means is that, so if I have a segment, A and B, and I have a perpendicular bisector to that segment, so this would be congruent to this, and this would be a right angle, that every point along that green line would be equidistant from A to B, okay? So there's an infinite amount of points happening there. That's what this whole thing means, okay? The locus is all those points that would be on that green line, and every single one of them would be equidistant from A to B. Those would be congruent. If I picked a point down here, those would be congruent to each other. All right, so this first example is how you'll use those things. Okay, it says to find the measure of MN. So if I look at that diagram, what can you tell me about it before we even get to MN?
It has a bisector.
There's a perpendicular bisector, right? What's the perpendicular bisector?
P.
Keep going, because P is just a point, right? P would be the midpoint. PN is the perpendicular bisector, right? Does everybody see that?
Yes.
Which means that PN hits ML, at its midpoint, which those two are already marked as congruent, and it's a right angle. It also means that any point along NP is equidistant from M to L. What does that tell you? These would be the same length. So MN is 2.6.
Wait, how did you get that they're the same length?
Because any point along the perpendicular bisector is going to be equidistant from the end points of that segment.
I have a question.
Mm-hmm.
It'll be what's it called? The points would be equal because you would be able to flip it over because of the bisector, right? Like if you were to flip it.
You can look at it that way. Yeah. I mean, you could go a lot further and say that those two triangles are congruent because it's side angle side, right? Because you got the reflexive side and then the other side and the right angle. Those two are congruent because it's side angle side. If I really wanted to go further, MN would equal NL because it's CPCTC. But we just don't have to do all that work anymore, okay?
What about hypotenuse? Like,
Now that we know that those are congruent, so now that we know the theorem and that that's a perpendicular bisector, you could have used hypotenuse leg. But before today, we didn't know that those hypotenuses would have been congruent. Does that make sense?
Yeah.
All right, B says find BC. So this time, which one's my perpendicular bisector? DA is the perpendicular bisector, which means it hits BC at a right angle, and what else does it do to BC?
It bisects.
Cuts it into two congruent parts. So if DC is 12, what does that tell you about DB?
12 too.
It's also 12. So if I want to find BC, just add them together. It's 24. Maybe you'll get an x plus 3 involved there. It doesn't really get harder. What gets harder is eventually we're going to start talking about angle bisectors, and they have a special relationship. And then medians, and they have a special relationship. And altitudes, and they have a special relationship. So you just got to, that's what I'm saying, by maintaining every day, learning what you're learning in that day is going to help you continue to move forward instead of trying to slam it all in at the end. So here we step it up a little bit, right? Because now we've got some algebra going on. So which part of this diagram is your perpendicular bisector? WU, which tells me that it cuts UV at the midpoint, which is already marked, and is a right angle. And what other information do we know? If a point's on the perpendicular bisector, then
But doesn't it cut, you said UV, UW. Did you say it cuts?
UW is the perpendicular bisector, so it cuts TV into two congruent parts, and it hits it at a right angle. But what other information do we know? That TU, right, would equal UV. Does that make sense? Right? Because U lies on my perpendicular bisector. So from U to the end point and U to the end point would be congruent. So 3x plus 9 would equal 7x minus 17. And then subtract the 3x. Add the 17. Divide by 4. X equals 26 over 4, or 13 over 2, or 6.5, or 6.5. Any of those answers work, okay? So 13 over 2, 6.5, or 6.5 would all work for X. But what's it asking for? TU, if I can stress nothing else to you, a lot of you made half credit on your test because you didn't read directions and you gave me X when it asked for the length of a side. So you want to make sure that if it's asking for TU, I do what? Plug it back in. So 3 times 6.5 plus 9. 6.5 times 3 would be 15, 19, and there's one decimal place. So 19.5. Yep.
And that'll be UV too, right?
Exactly. So you could have actually plugged that in to either one. And you can plug it into check to make sure it's right, because both TU and UV should be the same. All right, distance. So remember that the distance between a point and a line is the length of the perpendicular segment from the point to the line. So when we show distance, there has to be a right angle. If I had a point here and I wanted to show, or sorry, not a point there. Let's say I want to show the distance from the point at the top to the line. I have to have a perpendicular segment. That's how you show distance. Okay? I can't just draw any line. The shortest distance from a point to a line would be the perpendicular segment connecting it. It's the truest form of distance. And you need to know that, obviously, for these. So these are angle bisector theorems. What's an angle bisector?
It's a
line that bisects an angle.
A line, a ray, a segment that bisects an angle, right? Cuts it into two congruent parts, right? So these are now about an angle bisector. The first one is the angle bisector theorem, okay? And it says if a point is on the bisector of an angle, then it's equidistant from the sides of the angle. So I'm going to zoom in on that one. So from the diagram that is here, what's my angle bisector? PC, right? Ray, PC, and I know that because these two little angles are marked as congruent. So PC is the angle bisector. And what the theorem tells me is that any point along that bisector is equidistant from the sides of the triangle. So if I pick point C, then the distance from C to A and the distance from C to B, which have to be marked with a right angle, those two are congruent. So if I picked a point here, let's say I called this point D, then to show distance, I'd have to show a right angle here and a right angle here, and then those two would also be equal to each other. So in order to identify distance, you have to have a right angle. But if a point lies on the angle bisector, it's equidistant from the sides.
You can make it right angle if it's possible.
It'll be drawn already for you. But yeah, if you had to show distance, you could make a right angle. You'd have to make sure that it's...
Basically saying that BC will be congruent to CA.
Yep. Yep. So from the diagram that's there, AC would be congruent to BC. Or if I added on points here like M and N, and this was a D in the middle, that DM would also be congruent to DN. Okay? Any point along the angle bisector would be equidistant from the end points. I mean from the sides of the triangle.
Why are there theorems if we're not even going to do proofs and reasons?
You still have to justify your reasons, right? You still have to know that in order. So if you go back to example 1 and example 2, you wouldn't be able to do those if you didn't know, right? The relationship. Okay, so the converse of the angle bisector theorem. Again, flip-flop what we just said. So if it was before, if the point's on the bisector of the angle, then it's equidistant from the sides. Now we're flip-flopping it. So if a point is equidistant from the sides, then it lies on the angle bisector. So again, if I look at that diagram, this time I know C is equidistant from A and from B. So then I can say from this, my then would be that PC is the bisector of angle APB. Or APC is congruent to angle BPC. So you can see either one of those. PC bisects angle APB, or APC is congruent to BPC. And you guys have got to get used to 3 letters for an angle, because you struggle there a lot. All of these are going to have a shared vertex, which means you can't use a single letter to describe any of them. All right, and then if you look on the bottom, it says, based on these theorems, the angle bisector can be defined as the locus of all points in the interior of an angle that are equidistant from the sides of the angle. And all that means is that if I had an angle bisector, that any point along that angle bisector would be equidistant from the sides. So those would be congruent if they had little right angles. Those would be congruent. Those would be congruent to each other.
So once you prove everything first, can you determine, like, can you say, oh, that's the locus? Like, you can't say
The locus is just meaning that there's an infinite amount of points. So don't stress too much about the word locus. It just means that there's not a fixed number of points here, right? All of these points would be equidistant from the sides, not just 1 or not just 2 or not just 3. Literally every point from the vertex out would be equidistant from the sides. That's all it means. Okay, so here's how you'll use angle bisector. So A says find the measure of BC. So what can you tell me about that drawing there?
That AC is the bisector.
Good. AC is the bisector of that angle, which tells you?
BC is
Good. BC is congruent to CD, or C is equidistant from both sides, which means BC is 7.2. Easy stuff, right? Angle. So again, you guys got to work on wording. This means the measure of angle EFG. So the measure is what? What does measure mean? outside of this example, like without a number? What does measure actually mean? What's it looking for? A degree measurement, like a number, right? So this is saying find the measure of angle EFH. So EFH is this angle here, okay? Again, you guys struggle a lot with like the directions there. Given that EFG is 50, so if EFG, which is the whole angle, yep, is 50, then this one is half of that, which would be 25 degrees. Questions on either of those?
Yeah, can you explain how you got it?
Which one? Both of them?
Not in deep.
So if you look at the big angle, right, it gave me the whole angle is 50 degrees. And because these two are marked as congruent, I know H lies on the angle bisector, which means that this is now cutting that 50 into two congruent parts. So if I only want part of it, I cut it in half or divide by 2. Okay, and then this last one, find the measure of angle MKL. All right, so before we even get to the arithmetic part of it, what could you tell me about this diagram? Okay, you did it right. KM's the bisector, and you know that because? The right angles and? You need both parts, the right angles and the congruency marks, right? So because M is equidistant from the sides of the angles, I could say that KM is on the angle bisector, which means what about those two expressions? They're congruent. So 3A plus 20 would equal 2A plus 26. Subtract the 2A. A plus 20 equals 26. Subtract the 20. A is 6. Is that my answer? No. What did it ask for?
Plug it in.
MKL. MKL is this angle here. So I'm going to plug it in here. But would it matter which one I plugged it into? No, because they're both the same. And actually, it would be a good idea to plug them both in and check. So if I plug it back into that one, I get 12 plus 26, which is 38. And this is an angle, so it's in degrees. If I plug it back in to check, 3 times 6 plus 20, 18 plus 20, which is 38. So it confirms that my answer is correct.
Would you get points off if you forget like the degrees?
No, you just have to be careful because I will say a lot of you, like in the test, it said a congruent statement, which should have been like triangle ABC is congruent to triangle something. And you give me 3 letters, which 3 letters is actually a plane, not a triangle, okay? Or some of you actually put an angle degree, but if you're talking about a triangle, it needs to be a triangle. So stuff like that's important, but the degrees and non-degrees, I wouldn't mark off for.